All right, so today we're going to continue on with our 2D-NMR. Last time we went through a little bit of an intro, gave just a simple example of what a 2D-NMR pulse sequence might look like. 2 dimensions essentially means that there's 2 different time delays. There's the acquisition and then there's some evolution time. And we essentially acquire a series of one-dimensional FIDs, spectra, and then we do a second Fourier transform in the opposite direction. So it gives us our 2 dimensions, 2 frequency dimensions. Remember that, I guess, with the time domains, we have T1 and T2. So this is the acquisition, and this is this evolution time. And when we do the Fourier transforms, the T2 dimension ends up being F2, and the T1 goes to F1. And so typically the T2 domain has better resolution. Because we acquire more points in our acquisition time than the number of increments that we do in that second dimension. Oftentimes what they do, though, is if you have, so if you do less points, you can do this in the first dimension too, but if you have so many points, it comes down like this or something, you can add to the end of the FID, you can add a bunch of zeros after the FID, and then do the Fourier transform, and it essentially adds more points into the calculation. And so you can sometimes kind of get better resolution for the amount of data that you have by doing this. Yeah. So there's actually a lot of little tricks, and I don't know all of them, but, some of these, or you can do, there are different types of weighting functions that you can apply to the data to change slightly the shape of the peak. Like they have this, Lorentzian, I think, multiplication and a Gaussian one, and, some of them come down more like this, and then the other ones, I think the Gaussian comes down more straight and then flattens out here so you can get better resolution near the bottom of the peak. Or exponential is another one, because I remember we used to have to type FT, what was it? Oh, there was 3 different commands. But I think that we usually did like a exponential calculation. But if you change it to the Gaussian, and then there's some values that you can change in there, so you can, kind of optimize the peak shape as well. So I think there's a lot of things you can learn like that. All right, so so far we've talked just about 2 different variants of a homonuclear coupling experiment that's coupling protons to protons. Okay, we looked at the COSY 90, which has 2 90-degree pulses, which is kind of the standard, simple COSY spectrum. And we looked at the COSY 45, which had that second pulse being a 45-degree angle. This, I was reading this morning, this is oftentimes also called a COSY beta. And like we saw in this COSY beta, it narrows down the spectrum near the diagonal. So some of these experiments that narrow it by the diagonal, they do that also by changing the peak shape. And we could also get the sign of the coupling constant, which would allow us to identify geminal couplings versus vicinal. Okay. One thing I'm not really showing you through some of these is there are also, even at this COSY 45, there are some phase-sensitive versions, which essentially means if you had a doublet, then the cross peak would be, one would be positive and one would be negative, instead of what we've looked at so far as just kind of an absorptive peak shape. And from those phase-sensitive ones, you can also get coupling constant information. All right, so what we're going to do today is look at some other variants of this kind of the COSY type. We have this one, it's called the double, that's not even right. Should be DQF, double quantum filtered COSY. This is a long-range COSY. TOXI is total correlation spectroscopy, and then NOSY is an NOE variant. So that's going to show us through space interactions rather than through bond. And then if we get through that, we're going to start into the heteronuclear coupling experiments, showing coupling between protons and carbons. All right, so the double quantum filtered COSY, so let me write that in, double quantum filtered. And I'm not really good at all of the, I was trying to read it. You got to get in pretty deep to really understand all of what the double quantum filtering and things like this. So what this kind of does is it suppresses the big singlets and the big tall signals that involved in spin systems with less than two or less spins. So like if we had a CH and a methyl, it would kind of suppress those. And it also, again, kind of minimizes the amount of signal along the diagonal. Okay, so it suppresses the diagonal. And it's also commonly used as this phase-sensitive, phase sensitive. So in that case, you could, if you want, you can get the J value information. All right, so in these two, we've got a COSY 90 at the top. And we have the double quantum filtered COSY down here. Okay, and so what we might observe when we look at this, we see the cross peaks and the diagonal, but what we see is along the diagonal here, it can be pretty kind of messy along here. And notice where we have this big doublet here for the two. Well, actually, we looked at this before. I think that it was almost like a triplet. I think we did this in one of our. We did. Yeah, and when they did different solvents, remember they came apart as two doublets. Mm-hmm. But so we have this strong signal here that's only has one other spin, and this also has very broad peak shapes down at the bottom, right? And so we see these big tails going in both dimensions. So these things, and in this region too, right, we have some of these tails going off. But when we do this double quantum filtered, notice how clean it is along the diagonal, right? So off of this methyl group, we have almost nothing. And in here, where we couldn't really see anything, we can clearly see this kind of coupling in tight on the diagonal. Okay? So that makes this kind of a big advantage. We can even see in here as well. So I think sometimes this can be, if you have complicated spectrum with a lot of peaks close to the diagonal, which means you have peaks that are close together that are coupling, right? So they're off-diagonal peaks that show the coupling are kind of narrow in on the diagonal, then this can be a good experiment for that. Okay. All right, the next one is called a long-range cozy. Is also, I saw this morning in this book, they also call this a delayed cozy, partly because we add this delay right here. Well, I guess it's twice. It's here and here. Before the evolution, so we add these fixed delays. So I don't think those don't increment or anything, but what this does is it enhances the small couplings, so the small J values. Okay, so here's two examples here. This is the normal, this is the cozy 90, I guess. And we don't really see much here. Which way does this go? We could figure this out in a second. A, B. Okay, yeah, so, well, it says right over there. This is A and B. So A and B over here would couple to each other for sure, but look, they're right next to each other, and in fact, we can see that these are very second-order coupling to each other because the outside peaks are so short. Okay? But because they're so close, we really can't see the off-diagonal peaks here, right? Because it would be one coupling to the other. You'd essentially have a square like that. And so we don't see anything else. If we do this long-range cozy, and I think you could play around with the size of these delays, but we see a lot of we see some extra coupling. So here, what we can see, so before we were already seeing A to B, that's between here, but B right here also shows a coupling out here. And notice that these two are slightly offset. And so this one goes to C, and this one here, this one is going to this end, so to C, and this one is going to B. Okay, so this cross peak here is B to C. This is the metacoupling, okay? And this one here, this is E, so this is going to be D to E. So it's another metacoupling, which weren't really showing up in the cozy 90. All right, so this went to this side of that. Yeah.
Is the way that it enhances small couplings by basically ignoring the louder signal initially with that weight?
Well, no, I don't think, I think that, the coupling, the only coupling that we saw before was between, well, we couldn't really observe it, but that we would expect to be there would be between A and B. So I think that that's probably still in there, though it's still hard to see. I'm not really sure how it selects for the smaller J values.
Well, the delay would just kind of turn the volume down on the ones that you would like the more the what is it, the stronger
Maybe the stronger relaxation's kind of.
yeah, if it's because if you wait, everything like with the FID, you're not getting the first part. You're getting everything that's a little bit like quote unquote quieter with the oscillations, and so you're bringing everything down size wise. I mean, granted, obviously the long.
Yeah, but that would happen for both the strong couplings and the
Yes.
weak couplings. So I'm not sure if that's why.
Well, but does it happen at the same rate?
Um,
Because if it doesn't, then that would do it. But if it at the same rate, then it doesn't.
Or this could be like a deep math thing that I don't understand.
It could also be deep math, yeah.
well, I think it would have something to do with, as the signals process, right? We're going to have the large couplings are, going to be splitting much more rapidly.
Yeah.
So it may be that the delay would be, the size of the delay might be relative to how the size of those bigger couplings. So if you could make them like anti-parallel and then you give it a 90, then they go into the Z direction where the small couplings aren't processing as much, and so when you tip them, they're still in the XY plane or something like that.
That would make more sense. Yeah, I can see that.
So you'd have to kind of, and so maybe it is true. I guess this is the only example I have here that the short range or the large coupling constant, maybe this is suppressed here, right? And not just only enhancing these. So we may be getting more long range and less short range, but I'm not 100% sure of that. But I could imagine if you time this, I don't know what this one would really be doing, but this one to where those big coupling constants split and they're actually like opposite of one another. Then when you give the second 90, they're going to all go into the Z direction.
Cool. Cancel out.
Yeah, so they kind of cancel out.
Yeah, I could see that.
So yeah, I think it would probably be something more like that, selecting rather than just, toning down everything.
Okay.
That makes sense.
That's a lot more reasonable of an
Right,
explanation.
okay. All right, so really an interesting way to get long-range information, though, is this TOXI. So this stands for total correlation spectroscopy. When this first came out, it was more usually referred to by the names of the people. It was called a Hartmann-Hahn spectroscopy or something. But yeah, they always have to come up with something that's cool. All right, so the pulse sequence here is kind of similar, but instead of having a second pulse, they have this thing called a spin lock. And somehow it locks the spins in the XY plane or something, and so the signal can propagate while it's locked there. And so you can vary the length of this, and the longer this is, the longer it allows the spins to propagate along a spin system. Okay, so what's kind of cool here is that we can see the spins correlating to other spins that are kind of beyond the range of our normal scalar J couplings. Okay, so let's look at an example here. So we've looked at these kind of compounds before, And let's just start out with this H2. So H2, being next to the oxygen and being next to the ester, remember, was the most downfield signal in this spectrum. Okay, so if we start with this, so this is the H2, and we go along the vertically or horizontally, this direction, we see that it goes to H3, which we would expect, H2 and H3. In a normal cozy, we would expect that. But in fact, this one also goes to either H4 or H4 and H5. And if we go even further, it goes to both of the H6 protons. So in fact, we're seeing kind of coupling from H2 to H3 to H4 to H5 to H6. Right? So you might think in this case, you know, what good is this? Because it essentially shows everything coupling to everything else. But what you can oftentimes do is you can run a series of experiments where you're increasing the length of this spin lock. And so as you increase the spin lock, they're going to propagate further and further. So maybe for one value of the spin lock, it's going to, you know, be essentially like a cozy and only go to H3. And we lengthen it a little bit. Maybe it goes over to H4, further H5, and we have a longer spin lock. It goes all the way to H6. Right? So you can run a series of experiments and see how the signal is propagating from proton to proton through this spin system. So where this really works well is where we have multiple different proton spin systems. All right? So for example, we won't work through all of this, but in this case, we have this cyclic peptide, right? So notice that it's just all amino acids which create these isolated spin systems, right? And so if we just pick one of these, so for example, this amino acid right here, okay, this is ornithine, and it shows us over here. Here's the ornithine, the alpha proton. So here's the alpha proton right here. Okay, so if we can pick out, you know, this is essentially the alpha proton area, okay, and we can go horizontally, we can essentially have all of the peaks within the ornithine spin system all along this line. Okay, so here's alpha, beta, here's the beta, gamma, here's gamma, and here's delta. Right, so we see all of the signals for that amino acid in this line right here. It's not really telling us what amino acid is connected to another amino acid, but that's going to be true essentially for all of the different amino acids here. They should all have lines going across like this. So for example, as well, here is, let's see, which one did I do here before? Right here. Okay, so this is for proline. Okay, and we have several prolines. I'm not sure. I have this one circled over here. So here's a proline right here. Right? And so along this line, so here's the alpha. So that's right here, right? So it would be like right there. And then we see that we have 2 beta protons. Beta, they're diastereotopic because they're next to the chiral center. Then we have beta, alpha, beta, gamma. Here's the gamma over here. And I guess those are mostly together. And then we have the 2 delta protons, which are really diastereotopic, right there. So again, we can isolate all of the spins within a certain spin system. Okay? And so you can also, there's... Where did I not put that in here? Oh, I have it later. Okay, well, let's continue on with this one. And then I'll say, I'll show you in a few minutes that, you can look up, there are patterns. So for each amino acid, there's going to be a certain pattern of peaks that would show up, right? And so you can essentially identify what amino acids are there by all these patterns coming off the alpha protons.
That's cool.
Yeah. All right, so you're which is that still for the well, I guess they wouldn't really show it past those, but from the NH to NH would go to the alpha. I know that also do, I don't know if these are time dependent. I don't know if these, let me see. Oh, this is still from a 2D experiment, but these are the projections. Okay, so what they're doing is just cutting through, let's see here. Which amino acid they're doing here, protons. Gramoside S. The NH proton. Okay, so in this one they're starting with the NH proton, but I don't know which. Oh, is this for the beta, gamma, alpha? I'm not sure. Ornithine? Maybe. Okay, so what they're doing here, though, is they're starting off the NH instead of just the alpha proton, okay? And what they're doing is changing the mixing time. Like I said, you could run this series of experiments where you increase the size of this mixing time, the length of the mixing time, and allow the signal to propagate through more spins. Okay, so here is a mixing time of 20 milliseconds. So what we see is from the NH essentially to the alpha proton. Okay? We go to 40 milliseconds, and it's going from the NH to the alpha and to the beta and the gamma. Okay, 60, basically the same, but this is increasing. And I guess that's all we got there. And, do we have and we go up to 80, and this delta signal starts coming in. So alpha, beta, gamma, delta. I think it still might be the ornithine here. So we're going off the NH to the alpha, then to the beta, gamma, oh, that's a gamma, delta. Right, so we can run a series like this. So this could be, I think these are just slices out of a 2D experiment. But there is, when I was also a variant that is just a one-dimensional experiment as well, where you irradiate, kind of like the selective decoupling experiments that we learned about way back, or the difference NOE experiments we looked at. In this case, I think they irradiate on some proton, and then they can likewise look at changes as the mixing times change. Or maybe this isn't a difference in mixing times. This is just looking at each of these coming off of, so D. So this isn't the ring, so let's think. So this must be this proton. No, it's 7. That doesn't even make sense to me. Because those protons are not going to be at 7. Oh, that's going to be, it's not that. It's going to be this NH here, this amide NH. Okay, so for D, it must be that NH, and so this is going to go I guess it's coupling back, or it's going back in this direction. So NHs, oh, it says NHs right there. Okay, so then 2, 3, which way are they counting these? 6, I assume a 2. This must be 2. 1, 2, 3, 4, 5, 6. So here's going to probably 6, 5, 4, 3. There's barely anything for 2, though. And then for B, it would be the same thing, right? In B, well, they have B and C together here. But so it's, in each of these cases, it's going to be from the NH into that whole ring spin system. And so, so for B and C, we can pick out all of the peaks, and so we could identify them in our one dimension, our spectrum down here, which ones go together to each different unit, right? And we could see all 3 of these except for this one over here because it has no NH proton. So you could probably just line those up and basically assign all of these. Well, you'd have to know which NH is which, I guess, to be able to know which ring was which. And likewise, you could do these with different mixing times and look at the propagation from along the spin system. But in each of these, these are isolated spin systems where they're blocked by some quaternary center, right? So they have the amide carbonyls, which block coupling through into the next spin system. All right, so that picture in there, I must have just put it in separate. So here you can see I got this paper or something, or from a book or something, and so that one at the top, So it shows a pattern for a given amino acid. They had a pattern like that for all the different amino acids.
Oh, cool.
And so you can just go through, and if you were working on peptides or something like that, or maybe they even bigger, proteins, they have, just these patterns. And I think they probably even have computer, programs to identify these patterns within the spectrum.
That's dope.
Yeah.
So handy.
Okay, so this has all been what we call the scalar coupling or the J coupling. The next, that's not even, I don't have. So the next one we're going to go to is going to be about the NOE. Okay, so I'm going to start with this. This was a compound that I worked on when I first started my academic career. So I isolated this compound from a marine sponge, and we were trying to determine the structure. And in fact, there were 2 different compounds. Well, actually, there were 4. 2 of them had this same general structure, and 2 of them, I think, the chain was shorter or something like that. But 2 of them, I had, 2 of these that differed in the stereochemistry here of those where the methyl groups are. Okay, so we can just look at this cozy. We could pick out a few things, I guess. So here's, the aromatics down here. These 2 protons are going to be the protons for this double bond here. There's 2 protons here. They go to this double bond. If we look up here, we can see this looks like a diastereotopic pair of doublets, right? Because they're slanting towards each other like this. And those are the 2 that are, so let's say, call these H2. That's going to be the protons here. So these are H2, right? And they're just isolated next to the carbonyl and between that quaternary center, so they're just doublets. And there's going to be another set that's going to be important for what we're going to look at here between this doublet here and I think a doublet right in here, which is a little bit harder to see, and those are the H4 protons. So those are on this CH2 group in the middle in this ring between these 2. All right, so is that always on?
Camera thing.
Yeah.
I think so.
Oh, is it? All right. Here's the 2 methyl groups. All right, those are those 2. Just the 2 methyl singlets. Huh?
Just trying to think of why they're that far downfield.
Well, what are they at? They're like at 1.3 or 1.4 or something like that.
I was looking at the
The vertical one?
no, the ones at 7. I thought you had just added that blue.
Oh.
And I was like, there's no way. There's no way.
Don't question me.
Right.
Yeah, no, those 2 singlets that are upfield.
That makes sense, yeah.
Okay. And then we could I think this one here, I shouldn't put the red, is like this other methyl group over here. So that one's actually a doublet. Okay, so what we're interested in really is between these 2 methyl groups and the H4 protons, okay, that are in between them. Okay, but postdoc down at we'd like to know, why is that camera thing?
Pause and replay the last little bit, see if you can see yourself.
Yeah, that's okay. There. Okay, so here's the two possibilities for stereochemistry, right? These two methyl groups could be on the same side, or they could be on opposite sides. So cis or trans or syn or anti, whatever. Okay, and so what we are going to look at is the two protons. I should have drawn these a little bigger, but the two protons that are in the middle here, let's put one with a wedge and one with a dashed line. And we're going to look at the NOEs from them to see which of the methyl groups are close to them, okay? And we might imagine that, say, for this system over here, both methyl groups are up on the same side, so they might show NOEs to one of these protons but not the other. And in this case, the methyl group that's up might show an NOE to the proton that's up, and this methyl group's down to the proton that's down. Okay? So let's look in here. So here's the two H2. Those were those two doublets. And they're out here. But what we can see from them is right here. Oh, so the other part that I didn't tell you is that here's the two. Here, let's go back. What we can also see here is these two cross peaks here are between H2 and the two methyl groups. And so what we see is that both of these, which I guess is what we would expect, both of these are showing NOE just to the methyl group that's adjacent to them. Okay. If we look at the, where did I mark those? The H4, so here's a, oh, it says it underneath there, doesn't it? Here, let me move this up just a little. We have the two, excuse me, H4. Let me do this in a different color. H4 and H4, which is slightly overlapping there. If we go from this H4 up this way, notice this H4 is going to both of the methyl groups. Whereas this H4 over here doesn't have very much at all here, right? But what it does show is that this H4, I think, is going to H4A to H6. So those are the ones that are on the other side of the ring. All right, so this one, because both H4 beta, this would be H4 beta is going to this methyl group and to this methyl group, right? So all three of those have to be on the same side. And H4A, would be this one is showing to H6 over there. Let me think about this. H4. Right, this is going to 6 right here. All right? Yeah.
This is all the bonding for the back proton that we're talking about? The green one? Or the green labeled one?
Yeah, the green one here. So these two are the one that are telling us the most because they're showing, let me draw this a little bit bigger. Okay, so we're calling this 4B, and this is H4A, and we have this methyl group here and this methyl group over here. And H4B is showing NOE to both of the methyl groups, right, through space. So it means that all three of those are on the same side. Okay? Makes sense? So maybe to help this make sense, I wonder, here's the other spectrum. And so instead of seeing these two, or I guess they were these two really strongly here and here, in this case, we see one strong one here and one here. So they're crossed, right? So this would be the case where, here, let me draw this a little bigger too. Let me move this over here. I'm going to draw it. So this was B before and A, and now if I draw like this, in this case we have H4B goes to one methyl group, like here, goes to one methyl group, and H4A goes to the other methyl group. Right, and this one here still goes on to H6 as well. Right, so we know that that's the methyl group that's at the 5 position, right?
For this, you had to get really close to the baseline to see it.
Right, yeah, you can see that there's kind of these, it's pretty noisy. I don't think there wasn't a lot of sample, too.
That doesn't help.
So, yeah, what we do see is these noise lines, like going up and down here. So from these methyl groups, right, they're going up like this, and then there's these weird things going like this. So it just means that, you know, those cross peaks, you know, their peak shape isn't perfect, right? They come down and they kind of trail off in one direction. So when you lower the threshold to cut it across there, you're getting some of this kind of tail along the peak, because that peak isn't really symmetrical. So yeah, it can be useful for stereochemistry. You know, it could be useful sometimes in like peptides, going from an NH. Let's look back. Utah, new faculty there that was looking at the three-dimensional structure of DNA, I think, and he was using NOEs like this, and you know, it's in a helix, and so there's a certain distance where you can see NOEs from one turn of the helix to the next one, and they'd measure the size of these NOEs, and then they could model the structure and calculate how large the NOEs should be, and then so they'd have a calculated spectrum, and they'd match that to the experimental spectrum, and if the sizes of those NOEs didn't match, they would kind of iteratively recalculate, and they keep recalculating the structure until the the predicted NOE spectrum matched the experimental one.
There has to be a better way to do that. I mean, that's really cool that
Yeah.
they did that. There has to be a better way. But,
You said this was when you were in Hawaii?
No, I was at University of Utah as a postdoc. Yeah.
That's labor intensive.
Huh?
So that's labor intensive. Wow.
Right, but I think all that the NMR of those big molecules like that. I'm sure some of it is probably even more, automated now.
yeah.
But those spectra are so complicated. If you just look at the one-dimensional spectrum, it's just like like this, right? And they have to look at all the cross peaks and line everything up. And well, now because we have two-dimensional NMR, right? They can do three-dimensional NMR and things where you have three different axes, like a big cube, and
Cool.
yeah. All right. We're not going to go there. Okay, so the next thing we want to talk about is the heteronuclear coupling experiments. Okay, so we're going to separate these into one bond couplings and multiple bond couplings. Okay, we do have one more homonuclear one, which is a C13C13 coupling, but we're going to save that to the end. Okay, so we're going to look at this one bond couplings. So one thing we want to talk about first is what I kind of introduced this before, is this het core or heteronuclear correlation experiment was like the first one that came out, and this was what we call a C13 detected. All right, so we essentially pulsed on the protons in the beginning, we detected on the C13s. All right, that has the disadvantage of being much less sensitive, right? But we'll see in a minute that there was a thing that made the proton detected experiments complicated to do in the beginning. All right, so these two are proton detected. Or like I said before, because we did the C13 detected first, then the proton detected were called inverse detection. Okay. There's a similar thing for these multiple bond experiments. We had a long-range het core or another experiment called a co-lock. So these are C13 detected. And the HMBC, and there's another version of that we'll see examples of, which is called the HSQC. No, that is... Oh, I already have that up there. That's the one bond experiment, the HSQC. So these two are very similar. So this is a proton detected. Heteronuclear multiple bond correlation.
Makes sense, yeah.
There was one of the... All right, so here's just a kind of a contrast between the het core and the HMQC. So notice in the het core, our first pulse here, is on the proton channel. Okay, so we have two different channels, and we know that the protons are at a different frequency than the C13s are at, right? So we're going to pulse first on the protons, then we have some, other stuff. Here's our evolution, our increment that we're going to do. This looks like it's kind of like a spin echo or something here. And then finally, our acquisition is on C13. Okay. For the HMQC, we have noticed that, well, I guess the first signal is still on proton, but we're acquiring on the proton as well. So other things we might look at here is because we're acquiring on the top one, C13 here, this would be F2, and this would have more points. Better resolution on the C13 channel. Whereas down here, this is now F2, and so we're going to have more resolution on the proton channel, okay, which is probably more important, is better too, right? Because our proton spectrum is more likely to have signal overlap and stuff than a bunch of singlets. Because notice that both of these have also the decoupler is on during acquisition, so we're removing any probably any coupling in the actual spectrum, right? We're observing coupling through the pulse sequence, but when we acquire the spectrum, everything's a singlet, right? In the C13 channel. So what we also said is a C13 detection is going to be less sensitive. And this should be more sensitive. Right? Now the challenge is, if we're going to detect the signal on the protons, we really only want to detect protons that are attached to C13 atoms, right? We're looking for that coupling between the C13. And so most of the signal is going to be protons that are attached to C12, right? We want to look at the interaction to C13. So why are all of these like that now? So the challenge is that we need to suppress the signals for the protons that are attached to C12. Okay, so here's a few examples of ways to do it. So I think A is just a normal proton spectrum. So this is just normal proton. And we have here, so this is going to be the proton attached to C12. And these are what we call the C13 satellites. And these are the protons that are attached to C13, right? And they're being split by the C13. And those are the ones that we are interested in, right? Because they're showing the coupling information. Okay, so we need to be able to suppress this signal here in the middle. All right, so they have some different ways. You might be able to, there's ways to change the phase. Okay, so this is, or you might be able to just essentially kind of irradiate in the middle here. Let's see, they had different sequences to do these things. Let me read these. Conventional for A is a conventional proton one without suppression. B is what they call phase cycling, and so they don't do this so much anymore, but usually in any of these experiments to suppress some of the noise, they didn't do it like we've drawn it out, where they're always doing the pulse around like the X and the detector along the Y or something like that. one time they'd pulse on the X and detect on the Y, and then they'd pulse on the Y and detect on the Z, and they'd cycle through all the different phases on where they're doing their pulsing and their detection. And so this would allow them to subtract out or cancel out some of the noise. And so the next one, C, was with some type of phase cycling, and so you can notice that there's suppressing this quite a bit, but it's still kind of noisy in the middle. Oh, that's C. No, what are this? A, B. I'm doing this wrong. Oh, A, B. Oh, I'm doing this totally wrong. 6.5. Okay. B, C. Here we are. Is B is a phase cycling. C is what they called a bird pre-saturation, so that's a different kind of thing. And now we use what they call the pulse field gradients, and that's D. So you can notice that D is essentially has that center peak totally gone. And so they had to work through this and before you could do any proton-detected experiments like this, because otherwise this middle section would just dominate the whole spectrum. Okay, so let's compare some of these, and I don't know what. Okay, so the top spectrum is the het core. Okay, so this is the C13 detected. And so F2, which is the acquisition, is the C13. And F1, which is the increments, is the proton spectrum. Okay, and it looks like they just have a high-resolution proton spectrum drawn there. Okay, so notice that in this, and let's just look at the bottom one first. So the bottom one is that inverse detection, and so notice now that F2 is now the protons axis, and F1 is C13. Okay, so they're given the same information, but they're flopped over. Okay. So essentially, in these experiments, we just have the proton spectrum on one axis, C13 spectrum on the other axis, and so every peak just shows that one proton here, this proton, is attached to this carbon.
That's nice.
Okay, so for example, this proton, H4, is attached to this carbon. So that means that's C4. All right? And so you can just walk through and, show which ones are attached to which. So, of course, because it's unsymmetrical, there is no diagonal like there is in all those homonuclear experiments. However, we kind of see that we have this kind of slanting up in this direction as well, but that's just because the proton chemical shifts and the C13 chemical shifts kind of follow the same rules, right? The double bond protons and double bond carbons are further downfield, and the aliphatic ones are further upfield. Okay? Oh yeah, this was where we saw this one before. We talked about this already today. And notice in here, this is I guess it's in here, but we see these two doublets are overlapping into that triplet, right? So here's one proton signal here, here's a proton signal on the other side, and they each go to a different carbon. The other things that are really good for these experiments is that, notice here we have 2 protons going to the same carbon, right? So it allows us to easily identify the diastereotopic sets of protons. So there's one set. Here's another set, right? And so that's really good. I don't know if we have to talk about these joint head to tail. So sometimes when we're solving these types of spectra too, notice that this ipsenol is what you call a terpene or a terpenoid. You know what that means?
Mm-hmm. It's just a couple the carbons. I can see my organic textbook.
Yeah.
Showing it, but I haven't talked about terpenes in a while. It's just like yeah, that. Yes.
So they're essentially made up of this kind of isoprene unit.
Yes.
Okay? And so then that isoprene is attached to another one, like this. And so we can always count kind of like 1, 2, 3, 4, and then the next one goes 1, 2, 3, 4. And so we should have methyl groups on the 2 positions if we see how to count these. So this one isn't too bad, and it's actually just how they counted it already, right? But 1, 2, 3, 4, and there's no methyl group there. What am I doing here? Maybe, this is 1, 2, 3, 4, 5, 8, 9. So this one is modified because usually terpenes are either C10, usually kind of the smallest ones, and because they were smallest, I guess, before they knew the structures, they were called monoterpenes. Right? These are things like let's say like, I think it goes like this, like menthol. Right, so we could number these 1, 2, 3, 4, 1, 2, 3, 4. So there's a methyl group on the 2 position each time. So knowing this kind of thing can help you put your structure together as well. Because we know there should be kind of some repeating unit like that. All right, so that was a side thing, and we're pretty out of time. Let's just wait. So I have a series of spectra. These are all, I ran a whole bunch of spectra right when we got the Joel downstairs. And so I just, got on there, ran all these 2D experiments and everything. So I have a series here that are on, this is a monoterpene as well, and we should be able to count the if we start where there's this gem dimethyl, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So in this case, on position 2, what would be a methyl has been oxidized to an alcohol, but it has that branch at the 2 positions. So 1, 2, there's a branch. 3, 4. So that's one isoprene unit here. And then the other isoprene unit is over here. Right? They're just cyclized twice. Okay, so we'll walk through these next time. And then what do we have? I think, and then after that, we'll start working. Oh, we still got a few things to do with HMBC, and then the inadequate, and then we'll work some examples and stuff after that. Okay. So we've got the homework that's due on Friday, and then I will have another homework that starts adding in the 2D-NMR.
On Friday?
Yeah, and then we'll do that for another Friday. And by that time, we'll be getting to the end of most of the 2D-NMR, and we'll start planning for our next exam.
Great.